Hello everyone, welcome back to the third lecture of 11th week. We are going to discuss today digital data acquisition system, and we are actually discussing our module 5 where we are seeing the data acquisition system as a whole. Okay, this is the course on measurement and instrumentation. Before we actually jump into digital data acquisition, let's continue our discussion on multiplexing. And in the previous class we have seen TDM, which was time division multiplexing. Okay, let us see frequency division multiplexing. This is also important. We have seen that for long range data transmission and to utilize the timestamp properly, we have to go with another kind of multiplexing system, which is the frequency division multiplexing. Okay. In this kind of multiplexing system, several information can simultaneously transmitted using different carrier frequencies and employing different modulation technique. Okay. In the TDM, we have seen that we were giving some timestamp to different signals. Say for example, we were using say single channel divided in time. Say at 0th second, for example, we were transmitting say temperature, and 10th second we were again transmitting temperature, but in between say at 7th second we were able to transfer say pressure signal or humidity signal. Okay. Now, we are not using the time with better efficiency. What is happening is there is a lot more dead time. We call the unutilized time as dead time. All right. So, what we are doing is now we are not using this time division, but what we are doing is we are using a frequency division. Okay. Now, at the same time multiple signals can be transmitted because they differ from each other in their frequency. Okay. For that, usually we use a different modulation technique. In communication, if you are not aware, there are different modulation techniques. We have amplitude modulation. In the amplitude modulation, we call it AM. Okay, there is a carrier signal. Okay, and its amplitude changes depending on the, say this was my carrier signal. Okay, now their amplitude changes according to the message that it carries. Say the message is something like this. Okay, now this modulates this carrier signal. So, this is information. This modulates this carrier signal. Okay, and in the amplitude modulation, its amplitude is changing. It looks something like this. Okay, and then it is demodulated at the other end. Okay. Similarly, we can have frequency modulation where now the amplitude will not change, but the frequency of the carrier signal will change. Okay, like so, you can say that this is carrying some part of the information, this is carrying another part of the information, and so on. Okay. So, there is one more kind of modulation, that is phase modulation. Okay. Phase can also be similar to the amplitude and frequency, phase can also be modulated. All right. So, several information can be simultaneously transmitted using different carrier frequencies and employing different modulation techniques. Okay. Now, these can be recovered separately at the receiving end by using demodulators, and you may also use filters because in the way it may carry certain noise signals and all. So, some filter is also required. Okay. The basic approach of this FDM is to divide the total available bandwidth of a single physical medium or single channel into several smaller independent frequency channels, and independent message signals are shifted to different frequency bands using a suitable modulation technique. All the modulated signals are combined using a linear summing circuit to produce a composite signal for transmission. Okay. This composite signal is a kind of complex signal. Okay. The carrier frequencies used to modulate the individual message signals are known as the subcarriers in the system. Okay. At the receiving end, the composite signal is fed into a bank of band pass filter, for example. Okay. Now each band pass filter separates an individual frequency channel from the composite signal. Okay. The separated signals are then demodulated to recover the actual original message signal, and finally the recovered signals are distributed to their respective output channels. Okay. Now this is the crux of a frequency division multiplexing system. Okay. If frequency channels are placed very close to each other, it can result in inter-channel crosstalk, or we can call it signal interference. Okay. Now to avoid this, the channels must be separated by a small portion of unused bandwidth. Okay. Now what I am trying to say you that if the bandwidth is, if I decided to use the bandwidth completely and the signals are very near to each other, okay, it will cause signal interference, and therefore what we introduce is a guard band. Okay. Now these unused frequency region that I just mentioned, where I am now separating them in, this is a frequency, in, we are separating the signals in a frequency, okay, and these unused frequencies are known as the guard bands. Okay. Now guard bands help to prevent overlap and interference between the neighboring frequency channels. Okay. So you can improve the performance and reduce the crosstalk by using these guard bands. Okay. This FDM systems is very useful in the data acquisition system because it enables simultaneous monitoring of multiple parameters. So say three physical signals, temperature, pressure and humidity, for example, although please note that they are not suitable for low frequency or low bandwidth signals like temperature, pressure and humidity. They are mostly suitable for high frequency or high bandwidth applications, but right now I am giving this example just to understand. Okay. Now I have these three signals, okay, and in the TDM I wanted to transmit them over a single channel, and say at 0th time I have obtained the temperature data, and then I have to wait for 10 seconds to get the another temperature data. Okay. But here I can monitor all these three together. Okay. So this FDM makes it possible to monitor several data at a one time. Okay. It is useful for continuous analog signals. It avoids any switching delay like we have seen in the TDM. Okay. And they are very much suitable for long distance analog telemetry systems because of this frequency modulation in place of time modulation, okay, or time division multiplexing. Okay. So this characteristic of this FDM are their strength and their advantages. Okay. So the FDM, we have seen that simultaneous data transmission is possible, and in fact their detection is also possible. Okay. It does not carry any switching or sampling noise. Okay. Continuous real time monitoring is possible because of this reason. Okay. Simple reconstruction of these signals is possible at the receiver end using the demultiplexing circuit. Okay. And they are very good for high frequency analog signals. Okay. However, they have also different disadvantages, like one of the disadvantages that you have just seen, that it requires larger bandwidth. Okay. So what you are doing is, you are, along with their requirement of larger bandwidth, you are also placing some guard bands. It further increases its requirement. Okay. It has a complex filtering requirement. Okay. Crosstalk between channels is possible, particularly if you are not using any guard band to utilize the bandwidth more effectively. Okay. They are not efficient for low frequency signals, as I have just mentioned. Okay. And they have expensive hardware implementation, particularly the components that you have seen are actually costly than what we have seen for the time division multiplexing system. Okay. So let us see some other parts of the analog digital acquisition system. This is what we have seen is the multiplexing part. Okay. But there are several other components that we have seen in the previous lecture about the analog data acquisition system, like it has a calibration equipment. It is equipped with the calibration system. Okay. a pre-calibration is performed before each test and a post-calibration is also carried out after each test. Okay. So, for example, your analog data acquisition system is connected, or the first stage is a sensor or a transducer, okay, which is meant to measure certain physical parameter, maybe humidity or whatever. Okay. Now, the output is certain, say in some volt, okay, say 1.58 volt or 1.78 volt for particular physical quantity. Okay. Now, this analog data acquisition systems are equipped with a calibration equipment to check if the measurement is actually 1.58 volt or not. Okay. Now, if there is a deviation found in the pre-calibration, okay, now say it is showing 1.8 volt in place of 1.58 volt, okay, it is calibrated to 1.58 volt. All right. Similarly, a post calibration is done. So, this is done before the measurement, and after the measurement if you do again a calibration, okay, and then if you check that if 1.58 volt is actually reading as 1.58 volt or not, okay, or if there is a certain deviation, you can guess that the measurement that you have taken may not be correct. Okay. Therefore, a pre-calibration and a post-calibration is always required in any data acquisition system, and most of the acquisition systems are equipped with that. Okay. Calibration generally include millivolt calibration for of all input circuits, and it also involves shunt calibration of all bridge type transducer circuits. Okay. Analog data acquisition system also has a integrating equipment, because it is sometimes necessary to determine the integral or summation value of the measured quantity. Okay. There are multiple methods available to obtain the time integral of a signal, and an analog integrating circuit can be used for qualitative or approximate evaluation of the summation. Okay. However, the analog integrators may saturate or become overloaded during the operation, and they also generally offer low accuracy and stability. Therefore, digital integration techniques are preferred over this analog integrators because of their precision and reliable measurements. Okay. Analog data acquisition system also require visual display devices, okay, to continuous monitoring of the output signals. Okay. These devices include panel mounted meters, numerical displays, single or multi-channel CROs, and storage type CROs, etc. Okay. Cathode ray oscilloscope has become integral part of any analog data acquisition system, and maybe we can take this CROs in detail maybe in the next class. Okay. Then the older generation analog data acquisition system were also equipped with the analog recorders. Okay. Analog recorders are devices used to continuously record electrical signal in analog form. Okay. They convert the measured signal into mechanical motion of, say, like pen, it can be a stylus or a magnetic recording, to produce a permanent record of the output signal. Okay. They are commonly used in data acquisition, in the process monitoring and biomedical instrumentation like ECG signals, and some of the laboratory measurements also have this kind of analog recorders. Okay. There are different type of analog recorders, like we have the older generation has strip chart recorders, circular chart recorder, galvanometric recorders, and magnetic tape recorders. There are some other varieties of analog recorders as well. Okay. But the principle remains similar, that there is some portion or the mechanical part like pen or stylus kind of thing that is moving, okay, and recording the data continuously. Like in the strip chart recorder, the recorder signals, it records signals on a moving paper strip versus the time. Okay. Circular chart recorder uses rotatory circuit charts for long duration monitoring. The galvanometer or galvanometric recorders are based on the deflection of a galvanometer mechanism, which is based on magnetic field that we have seen in our previous discussions. Okay. In the magnetic tape recorders, they have the capability to store analog signal magnetically for further analysis at the later stage. Okay. But the key characteristic of all these devices remains similar, that is they are continuous, they have the capability of continuous real time recording of the signal variation. Okay. They have limited frequency response due to their mechanical inertia. Okay. Some may have better, like for the magnetic tape. Okay. They have moderate accuracy level compared to the digital systems that are available nowadays. Okay. And permanent visual record are useful for later qualitative analysis. Okay. And that is why these recordings were done. Okay. However, since there is a mechanical movement involved, they have low precision and low resolution. Okay. There is always a chance of mechanical wear and tear, and there is always maintenance issues with this kind of recorders. Okay. And they have limited storage speed and bandwidth capabilities, and therefore they have limited use. Okay. There are only a few places where they are still relevant, like in the legacy industrial plants where old instrumentation systems are still operational. There you will find these analog recorders. Okay. In process industries like power plant, chemical plant which has not upgraded itself, okay, for simple trend monitoring, these analog recorders are still functional. Okay. In the biomedical setup like older ECGs and physiological recording systems, these are still relevant. Okay. In the field measurements where rugged, simple, low power recording is needed, these systems are used. Okay. And further, for educational and demonstration labs to teach basic instrumentation concept with the capability of logging the data on some chart or store it magnetically, these devices or these recorders are used. Okay. Then some of the systems also consist of analog computers. Of course, now it has been almost obsolete. Okay. However, we should know that what were the analog computers and how it became an integral part of analog data acquisition system. Okay. So, we have seen that our data acquisition system records signal obtained from the first stage, which is a sensor or a transducer. Okay. It also processes and reduces the data into the required form. Okay. Now, you have an analog computer at this stage which can used for data reduction and further signal processing. Okay. The output of analog computers is typically a voltage signal, and this output can be recorded directly in a analog form. Okay. Alternatively, which is done right now, it can be converted into digital form for storage and further computation. Okay. Now, largely these systems are obsolete in modern instrumentation. Okay. And they are replaced by digital computers, microcontrollers, different DSPs and software based processing systems. Okay. However, this analog data acquisition system itself has certain limitations. Okay. But they also have different advantages. Okay. Like if you see, the analog dash has a simple design, you do not have any quantization error here. Okay. And they are good for real time visual observation. Okay. And the initial cost, the basic system cost is low as compared to a digital data acquisition system. Okay. However, they have different disadvantages also, or different, I would say, limitations also, like they have difficulty in long term storage of data. Okay. You are not having any system here to, you have system for continuous monitoring, but for long term storage you need something else. Okay. They are very much noise sensitive. Okay. And their accuracy level is less as compared to the digital data acquisition system. Okay. No easy data processing is possible because you have not done any processing, post recording processing, I would say. Okay. And most of them involved a manual analysis. Okay. However, they are still relevant in early instrumentation system, in the laboratory oscilloscopes, analog control system, and in the traditional audio signal processing systems. Okay. Therefore, seeing its limitation and their limited application, it is very important to understand the digital data acquisition systems. Okay. I have been telling continuously that the real world signals are mostly analog and continuous in nature. Okay. They are also, because of this, lot of noise is also there in these signals. Okay. However, our computers understand the digital signals either 0 or 1, and therefore, we need to convert these physical signals into certain digital data. Okay. Now, a digital data acquisition system, or I would say D dash, is a system that measures physical variables, convert them into digital form, and has the capability to process and store them, and of course it can also display. But the processing capability is very important, and this enables it for further analysis. Okay, so for example, if your sensor is giving certain input and you have continuously measured over certain time period, say for 24 hours, okay, or say over 30 days, okay, this digital data acquisition system has the capability to store the 30-day data, okay, and provide you with all the sensor parameters, including the sensitivity, selectivity, hysteresis, and so on, okay, because they have the capability to analyze the data as well. Okay. Now, this is a typical digital data acquisition system. You have a physical quantity, maybe anything varying like temperature, pressure, and so on. You have a sensor, a signal conditioning circuit, okay, a mux, and signal converter, and a sample and hold circuit before it is fed into AD converters. And what you can do is the output of this AD converter can be stored and displayed. However, you also had a digital processor or computer where this data can be further processed, okay, which was not available in the analog data acquisition system. Okay. Working principle of these systems are very simple. You have physical parameters which are measured by the sensor or the transducer at the first stage. You have these sensors convert the whatever physical parameter is there into some electrical signal, maybe it's a voltage or a current, okay. Then in the next stage it is fed into a signal conditioning unit where it improves the signal quality, maybe by amplification, by filtering, or by isolation, okay. Multiplexer select the required input channel, okay, and further you have a sample and hold circuit which captures the signal and hold it for the ADC to convert this analog signal to digital data, okay. Now, you have a digital processor which can help in analyzing the data, and it can help in storage and further processing of the data, okay. Of course, at the same time you can also display the data, okay, and use for whatever purpose you are using it, okay. Maybe it is basically providing you with a active control system, okay. The basic block diagram of a digital data acquisition system looks something like this. You have this transducer, signal conditioning equipments, multiplexer, converters, AD converters. Signal converter may be at the depending on the frequency, you have a sample and hold circuit also. You have a digital recorder, and this is all connected through a auxiliary equipment and a system programmer, okay. So, we have seen that the job of this sensor is very similar in both the cases, where you have input as some physical quantity, maybe time varying humidity, time varying temperature, and so on, but the output is say less amplitude or low amplitude, noisy, non-linear signal, okay. Then the output is fed into the signal conditioning circuit that we have already seen, okay. So, signal conditioning is done where you can do number of things. You can do amplification, you can do filtering, isolation, and if linearization is needed, then linearization also, okay. Then you had a mux circuit. We have seen that in the analog data acquisition system also, that when you have multiple inputs, this mux helps you in selecting one of the input and feeding it to the further circuit, okay. So, if you have multiple components, like if you have three sensors, say temperature, pressure, and humidity, mux will select one of them and fed into the next component, okay. So, what it does is basically it reduces your hardware cost. You do not need to connect each of them separately, and it is helping you in reducing the hardware cost as well as simplifying the design of your circuit, okay. Then you had a signal converter, which converts or which translates the analog signal to a form acceptable by the analog to digital converters, and it goes through sample and hold circuit. Okay. The sample and hold circuit captures the analog signal and hold it constant during this conversion. Okay. The operation of sample and hold circuit we have seen previously. Let me quickly recap it for you. The operation is in two modes. You have a sample mode and a hold mode. In the sample mode, the circuit samples the input signal, while in the hold mode, the signal value is held constant, so that in this period the analog to digital converter does its job. Okay. So, if the signal is changing rapidly, without this sample and hold circuit, you will have inaccurate conversion, and with the sample and hold circuit you will have accurate digital output, because when the sample was or the input was changing, at the same time ADC was converting, so it may give you your erroneous results. All right. Then you had ADCs, which converts the analog signal into digital form. Okay. Mostly in the binary form, we have seen this in detail, like this is a 4-bit converter where the analog value is converted into different 4-bit output. Okay. For different parameters important for ADCs we have seen, like resolution, sampling rate, and so on. Okay. These parameters becomes more crucial when you talk about digital data acquisition system. Okay. Then you have a digital processor, or you can say a PC or a computer, where when you have the output in the digital form, the signal is now ready for further processing using, say, microcontroller or a digital signal processor or this computer that I am talking about. Okay. Function is very simple: to process the data, to analyze the data, control the action, store the data, and display the data. Okay. Storage and display is another important thing with this digital data acquisition system. Okay. So, after the processing, the data can be stored in different magnetic memory devices like hard disk. In other devices, maybe in the modern digital DAC systems, you have cloud storage as well. Okay. Then display is also possible with the different available monitors, specific LCD displays, and different graphical interaction. Okay. This digital data acquisition system can be of different type, particularly in the modern scenario. This is changing, and new digital data acquisition systems are proposed every year. Okay. So, based on channel, you have a single channel digital data acquisition system, you have multi-channel digital data acquisition system, you also have distributed digital data acquisition system, we have multiplexed, or we sometimes called time shared digital data acquisition system, we have parallel digital data acquisition system, and real time digital data acquisition system. Okay. I mean, this number is not complete. There are other type of digital data acquisition system. Okay. Now, let us understand some of them very quickly. Okay. So, I am telling you very quickly because most of them you have already understood from our previous lectures. Okay. Like single channel data acquisition or digital data acquisition systems have only one sensor or one input signal is connected to the data acquisition system at one time. Okay. The analog signal from the sensor is directly processed and converted into digital form, and this is typical thing that is happening. You have a sensor, it is fed to the output from the sensor is fed to the conditioning circuit and fed to the ADCs, and then it is fed to a computer or display for further analysis. Okay. The system, if you look, is very simple, and of course they can be easily implemented at even lower cost. It is used when only one parameter need to be monitored, like if you are monitoring only temperature, or if you are interested in only monitoring, say, humidity. Okay. These are actually much simpler circuit for laboratory demonstration and other things, but multi-channel digital data acquisition system is what mostly you will see at commercial level. Okay. Here you have multiple sensors, they are connected simultaneously using a mux. Okay. The selected signal is then sent to a sample and hold circuit and ADC for further conversion into digital data. Okay. Now, this multi-channel digital data acquisition system allows monitoring several physical parameters using a simple single ADC. Okay. Example can be like environmental monitoring systems, where you are monitoring several environmental parameters, like you are monitoring CO2, you are monitoring CO, you are monitoring humidity, you are monitoring temperature and so on together continuously. Okay. Similarly, in the industrial process control and biomedical monitoring systems, where you are measuring multiple physiological parameters together, okay, these multi-channel digital data acquisition systems become more important. Okay. Then we also have distributed digital data acquisition system, and this is more logically correct systems in the modern scenario. Okay. In this system, the data acquisition units are placed at different locations. When I say different locations, I mean to say that different geographically distributed places. Okay. Now each unit collects data locally and transmit it to a central computer or a control system. Communication can occur through network cables. It can also happen through wireless system or industrial communication protocols. Okay. Now these systems is useful when sensors are spread over a large geographical areas. Okay. Example can be a power plant monitoring system, where the sensors are distributed across the plant, maybe a 30-acre plant or 40-acre plant or so on. Okay. Similarly, in the smart grid systems, this distributed digital data acquisition system has found its importance. Okay. Similarly, in the weather monitoring stations, you can monitor it remotely. So now we have different remote weather conditions, which all these remote weather stations transmit their data to a centrally controlled computer, where this data is further processed. Okay. We have time shared or multiplexed digital data acquisition system, where multiple analog input signals from sensors are connected to a multiplexer. The multiplexer select one channel at a time in a sequential manner, and this selected signal is passed to a sample and hold circuit. Okay. The sample and hold circuit holds the signal constant during this analog to digital conversion. Okay. A single ADC is more than enough to convert this. Okay. Digital output is stored, processed or transmitted. The process repeats rapidly for all the channels, and it appears simultaneous. So it's basically very similar to what we have seen in the multi-channel digital data acquisition system. Okay. Then we have parallel digital data acquisition system. Okay. Here analog signals from multiple sensors are directly fed to individual ADCs. Now earlier you were using only single ADC. Here you can use multiple ADCs, but why this is done? Because to improve the timing response of the system. Okay. Here it will be even faster that we have seen in the previous case. Okay. So all channels are sampled at the same instant, means the simultaneous sampling is being done. Okay. Digital outputs are processed or stored in parallel, and synchronization is maintained using a common clock. Okay, to all these channels. Okay. Then we also have a real-time digital data acquisition system in the modern systems. Okay. A real-time digital data acquisition system is a system in which the measured data is acquired, processed and used for decision making or for any kind of control immediately without a specified time constant or any specified time delay. Okay. Now this kind of systems are widely used in further automatic control, for monitoring and for safety critical applications. Okay. In these systems, the sensor measure physical parameters, for example, say temperature, humidity or vibrations, and analog signals are conditioned using signal conditioning circuit, and these signals are converted to digital form using high speed ADCs. Okay. Now this digital data is processed instantly using a combination of say processors, controllers, DSPs and in the modern VLSI with FPGAs. Okay. Based on the processed data, control signals are generated and actuator perform the corrective action in real time. And this is what our goal was, to monitor this data or to take action in the real time. Okay. The process repeats continuously, forming a closed feedback loop. Okay. So, this is in very brief about the digital data acquisition systems, okay, and of course, they are more relevant in current world than the previous generation analog data acquisition system, and their applications are across industry, in the biomedical system, in the laboratories, and even in the space and aerospaces. These digital data acquisition system has found its utility, okay. They possess several advantages, like they have high accuracy, easy data storage is possible, automated operations can be done using this digital data acquisition system, real time monitoring of the data is possible that we have seen, and at the same time real time control and decision making is also possible, okay. Data analysis becomes very easy because this digital processors help you, and the manual intervention becomes very limited, okay. However, the initial setting up cost is very high. So, this you can say that one of the limitation is of this digital data acquisition system, okay. They require proper calibration, pre-calibration as well as post-calibration, okay. Conversion errors may happen, and they require a complicated digital processing hardware. That is why I mentioned that the initial setting up cost of these data acquisition system, digital data acquisition systems are high, okay. So, with this, I hope that you have understood the digital data acquisition system as well as the analog data acquisition system, okay. In the next class, we will continue our discussion on some of the component of this data acquisition system that we have not seen previously, like the CROs. Thank you.